So today is probably one of the first BC lessons that are only BC and would not be touched on by AB at all. So the first one, phi 1 shell method, is really just a different way of finding the volume of a region revolved around an axis. Euler's method is a method for approximating a y value based on a differential equation. Integration by parts and the lessons that follow it will teach you about how to use integration in a way that does not come up in AB. So, the main idea of integration by parts is that it's a method for use mainly for products of algebraic and transcendental functions or products of two transcendental functions. E of x, e to the x, and sine of x are both transcendental functions. In general, we have a list of them. I'll go over it in a minute. It can be used for other situations. I have a way I like to go about choosing how to go through it. The idea is, while in AB, one of the things I say most frequently is there's no product rule for integration, which just means no, not this, right? This guy is not equal to that. They are not the same thing. And if you're taking the BC test, you need to know that. However, there will be something we can do to show it. Now, if these two are functions, this is a product rule situation, a product rule for differentiation. So the way we would get the product rule here is something close to u u v prime first times the derivative of the second plus second times the derivative of the first. Or, what we really mean by that is u times dv by dx plus v times du by dx. So that what we can do here is, therefore, since these two things are equal, their antiderivatives must also be equal. Right? And the antiderivative of two things added together is the same as the antiderivative of the sum of those two things. Take it by dx, I'm sorry. So u and after some quick simplification, this is an integral of a derivative. Integral of a derivative kind of cancel each other out. And we just have uv. That always happens when I first boot up the computer. I'm sorry. U dv plus the integral of v du. So what we've effectively shown is that u times v minus the integral of v du is the integral of u dv. And this is what integration by parts is about. It's finding a way to turn the product rule for differentiation into a new formula for integrals. This is an integration formula. If I have an integral of this form, I can transform it into an integral of this form. Okay? Now that's very powerful. You're changing one integral into another integral. And hopefully the idea is that this integral is much easier to do. So if you look at down on the page, this is what we have. And again, the goal of the whole thing is that this guy was impossible, and now you've gotten this is easier to integrate. And easier can mean a variety of things. It usually means you can integrate it, whereas this was something you cannot integrate. So as always, excuse me, as always in chapter 6, we are dealing with something that is about using your integration skills in a new or unique way. You need to be able to identify integrals correctly. It's a huge skill in AB. It's an even bigger skill in BC. So please make sure you have your ducks in a row while you're going through this. The basic idea is, oh gee, everything else I tried doesn't work, so we're going to stick with this. One way I tell students to try to remember this is this acronym right here, ultraviolet voodoo. Why? UV is a synonym for, well, not a synonym, an acronym, I think, for ultraviolet. You'll see, like, on the sunblocks, UV protection. And then that kind of looks like voodoo. And that's just a mnemonic, a memory technique to remember the formula. Ultraviolet minus integral voodoo. Or ultraviolet voodoo. This is usually enough to get you guys going. You guys have some capacity to memorize. Alright. A brief word. Let U be the part whose derivative is simpler, or at least no more complicated than U itself. So the idea is U is something that is easy to differentiate. U is easier to differentiate. And then dV is the part that's more complicated, or at least the part that's easier to integrate. Right? To go from here to here, I have to differentiate. To go from dV to V, I'd have to integrate. So, you all typically have only two choices. If one choice doesn't work, you can try the other. The other thing is a strategy I learned from my calculus textbook in high school. The integration by parts test was the only test for which I beat my friend 99. If you don't remember, 99 was a friend named for his lowest grade on a math test was 99 one year, which was somewhat annoying to all of us. And the only time I ever beat him on a test in calculus, or at least one of the few times, was after being sick for a week, having my wisdom teeth out. I had to learn this from the book, and the book told me this. Liate. 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 I don't know. Sounds silly? So you're going to choose U in this order. Logarithmic functions first. ln x. I don't know where you guys are at in terms of your understanding of what is what. So that's like ln x would be my top choice or something with U. Inverse trig would be like something like arc tan x. Algebraic, we're thinking of polynomials. Easy to differentiate, easy to differentiate, easy to differentiate. Hard to integrate, hard to integrate, hard, no, in the middle. Trig refers to, you know, your classic friends, sine x, cosine x, etc. Oh, I want to make ellipse, okay. And exponential functions, e to the x, okay? So, this is my first choice for you. First choice. Last choice. Or at least very roughly. For you. For choosing you. So, it turns to problems that, at least to me, start off as somewhat being unintelligible into ones that are really easy to do using this idea. So I look at example 1. Again, we can think about who is easier to integrate and who is easier to differentiate. Now, if you're good with your integration skills, you should think both functions, x and e to the x. I'll make that clear that these are the things we're concerned about with integration by parts. There's two functions here, x and e to the x. Okay? I have those two functions. One of them is going to be u. One of them is going to be dv. So, if you're good with your integration at this point, you know that they're both relatively easy to integrate. You should be able to take the integral and the derivative of e like that. I can snap with the other hand. And you should be able to take the derivative and integral of x like that. Now, one is better. One is better here. And the one that is better is algebraic. X is an algebraic function. X is a polynomial function. So u equals x. And if that's u, then the derivative of u is 1, or dx. Likewise, so that means everything else has to be dv. Will be e to the x dx. And again, this is what I mean. If you're sitting there writing down an integral for this, you are not ready yet. E to the x. You should be able to do that in your head. So for me, that means this integral, our original boring integral, we break it up into ultraviolet voodoo. Now, do not get confused, guys. This is not saying these are equal. It's equal if you subtract this part. And we had to prove this. This is a rule that came from the product rule. It doesn't just come out of nowhere. It doesn't just, oh, now integration's easy. Now I get to use a product rule. No, it's complicated. There's a twist. But this is an integral that's easy to do. That's already outside of the integral. So our final answer should be x e to the x minus e to the x plus some sort of constant for integration. And that's all there is to it at the end of the day. Alright, let's see a harder problem then. X times sine 3x. Again, if you are good, you know both of these are pretty much easy to integrate and differentiate. Now, it's harder for you AB kids who are jumping because you haven't had 5 units of experience differentiating and integrating sine. Again, I urge you to go study those topics before you continue on these videos. Memorize that sheet. Just pull out the sheet now while you're going through the video at the very least. There's a whole sheet I sent you during the 4-day weekend. Memorize these formulas. You need to know all the differentiation and integration formulas pretty much by heart. Here we go. Now, you might have a box on your notes, and a somewhat empty box, I don't know. Let u equal, again, if you were questioning which one to choose, it's going to be x, because x is algebraic. Li a te. T is trig. So then du equals dx. We will similarly let dv equals the rest. This whole part is dv. Any leftover bits have to be grouped into dv, including the dx. So dv is sine 3x times dx. So therefore, v would be the integral or the antiderivative of this. So the antiderivative of sine, well, yep, it's cosine. It's negative cosine. And in fact, it's negative 1/3 cosine to make sure this hooks off right. You need like a little hook off. And again, The people I was expecting to get a 5 on the AB are likely to be the people watching this video. So please make sure you are getting to the point where you can do that in your head a bit. For the simpler ones, like this. Like, oh, I need a hook off because of the chain rule. Because this guy has an inside, I need a hook off. What's the hook off? 1/3. Or it produces, the hook off is 3, so you need a 1/3 on the outside. Massage it to be that. Okay, here we go. So, alright. So our original integral is u v, and yes, you could write this in a different way, be just as nice, minus the integral of v du. Now I said du, but I wrote dx because du is dx. Ultraviolet voodoo. Okay? Now I'm going to simplify this a bit, clean it up. Green? I haven't used green yet. Negative x over 3, cosine 3x. Negative and a negative makes a positive. 1/3. I don't know. Let me show you this. I'd like you guys to get good at pulling out those constants. There's no reason to keep them in. I mean, unless they're going to be hook-offs, but we know 1/3 is not the hook-off in this situation. Instead, I look at the inside. The inside is 3x. The derivative of the inside would be 3. So in fact, I need to hook off another 3, which will produce another factor of 1/3. So in a moment, you're going to see a 1/3 pop in out of nowhere. That's where it's coming from. So that's that 1/3. And then this integral requires another 1/3 in order to become a hook-off. Sine is the integral of cosine. Oh, oops. Plus. Now, again, if this is still mystifying to you, which it might be, because you guys haven't seen it for 5 units, the derivative here, the derivative of cosine is negative sine, but we already have that negative to take care of. And then I would take a derivative of the inside times 3, and that would kill the 1/3. So that's where these are coming from. And yes, you could simplify this further. We're just going to leave it. Arc sine. What is the integral of arc sine? Should you know it already? It's hard to tell. No, you shouldn't. This is one of the more surprising facts of integration by parts. Before, and in AB, you'll see a lot of your AB peers will never ever learn that you can integrate log, that you can integrate arc sine. You don't just need hook-offs around them, you can do it with this technique. So here I go. I think your homework might ask you to do arctan. So, be ready. This is an important method. You should rack your brain. If you see this on the test, you're like, oh God, oh God, oh God. How can I integrate arc sine? And then there's nothing you can do. Some people will think it's cosine or something crazy like that, or arc cosine. It's not. They're not related that way. Whose function can you differentiate to get arc sine? Nobody. Well, you're about to see somebody, but none of the standard functions you see in Calc 1. So, what are we going to do? We're actually going to try something a little crazy. This is an inverse trig function, the I in Liate. Let u equal the entire trig component, the inverse trig component, du. Hey, we just did this lesson. What a crazy random happenstance. What is the derivative of arc sine? How well have you done your homework up until this point? Have you done the homework for 6-2, or are you just trying to blow through these, thinking that all it'll take is watching these videos? Because if you don't know this cold, it's going to hurt. The BC test is going to be painful. You'll have to learn these. The derivative of arcsine is 1 over the square root of 1 minus x squared dx, potentially. We all should have that. So that's the u part. Now who would be dv? Who's left for dv? Who can dv be? Well, there's only one little guy left, dx. And when you first see this, that should look crazy to you. You should basically be like, what the heck is that? That seems like a goofball tactic. I don't know. It seems like fake math. It's not. It's very, very rigid. There are things that you and your peers do that is fake math. This is not. This is following the formula. If you look at the last two problems, dx was always part of dv. So there's nothing else left to be here. Maybe it's 1 dx if you want to write that. That's fine. And now let's just follow this formula. Let's just follow your nose, guys. I'm so sorry. One day these will be great. I promise. So we have ultraviolet, UV. I got this. X. Arcsine X. Mr. Leven, you said UV and you just wrote VU. Well, U times V is the same as V times U. 3 times 2 is the same as 2 times 3. Right? Multiplication is commutative. So we can do it like that. Minus integral. VU. And in this case, I will write it out that way. VU. Do. And now you're looking at that saying, oh my gosh. What the heck is going on? At least this is done. Let's write this out in a much nicer way. Let's write this by multiplying x into the top. Multiplying x in the top. I'll just write it out. I was going to erase it, but let's just treat you guys like royalty. X arcsine x minus integral x over, because this is a much nicer thing to look at. Because you should not have been thinking, oh, I'll do integration by parts here. That's wrong. It's very wrong. Instead, and this is where you have to be getting to be able to do the BC test at the highest possible level. And again, you guys don't need 5s to take 252. You need 4s. 4s will get you credit at almost every college. EC credit is usually much better to get. And colleges recognize it more freely, let's say it that way. So the thing I want you to be able to recognize here is that I see a group to a power. I see a group to a power on the bottom. And the derivative of that group would be negative 2x. And wouldn't you know it, I have the x laying around to be the hookoff. So I'm going to rewrite with this group to a power on top, like we always do. Arcsine Alright, here we go. I'm going to leave a space, hint, for stuff. Here we go. Like that. And again, what was the derivative of the inside here? It was negative 2x. So I need to give myself some hook-offs here. Negative 2. Right? And that's going to be a hook-off. And to get that negative 2, I need a negative 1/2 on the outside. Capiche? Got it? Cool. Now, what form is this? I know a lot of people still struggling to know which kind of integral is this. It's the reverse power rule. The reverse power rule. Some people still have a tendency to call it the reverse chain rule. Again, they're all reverse chain rule. So, all told, x arcsine x plus 1/2. I'm going to increase the power by 1. Negative 1/2 plus 1 is positive 1/2. And I do have to divide by the new power plus c. Now, nobody in their right mind is sitting there thinking, oh, I bet you this is the antiderivative of arcsine. You have to do this work. I am not telling anybody, BC kids, AB kids, to memorize this. That would be a really silly thing to do. Okay? Alright, guys. Next. Alright. Product of an algebraic polynomial with a trigonometric. Right? A-T. Liate. So, let's just follow our nose. And again, if you look at each of these examples so far, none of them could have been done with traditional integration techniques. There's no hook-offs here. There's no nice relationship. Alright, so u is going to be x squared. Du would be, good job if you said or thought, 2x dx. dv would be everything else. Everything else is dv, including the dx, as we just saw. And I know you guys are just trying to get used to integration with trig. V equals, the antiderivative is negative cosine, and you need that 1/2 there to counter for the inside hook off. What I mean, if you took the derivative here, derivative of cosine, negative sine kills the negative, times 2, because of the hook off, kills the 1/2. And we can go backwards too. Always can check your work this way, guys. And now when you do that integral, kiddos, you got, hey, that's right, u, v, 2. There we go. Minus the integral of v du. And I'll clean up things. I was like, sorry. So I'll clean this up a bit. But you should already be thinking, there's a problem here. What is the problem? Donde problem? It's actually quite pretty right there. That's all outside the integral. We are overjoyed to hear. This time I'm doing 1/2 times 2. 1/2 times 2. The negative and a negative are becoming a positive. Okay. I could take all the constants out, but I'd still get a 1 on the outside. And indeed, I'm getting x cosine 2x. Now, in case you are confused about what's happening, my children, this is also not something that you can integrate without integration by parts. This is also a non-traditional integral. This is not a nice integral. It's not an easy integral. This is when we have to think about, and we'll have to think about this by parts again. Yeah, here we go. So this time, let's just call it U2. Still the algebraic part. It's still algebraic versus trig. Liate would be x. So du2 would be dx. dv2, sometimes we arrange it like this when we're running out of room, cosine 2x, blah. And so v2, the antiderivative of cosine is sine, and I need the 1/2 for the hook off here. Again, you will see me teach you trig if you haven't seen me do this before. We're doing it soon. It's sooner than you want, probably. But it's coming up. Don't worry. You'll understand. You'll become good with trig. You have a whole another month to become good with trig. And then a whole another month after that to let it all coalesce into perfect calculus knowledge. Alright, guys. This part's still the same. Don't forget to carry it out. Carry it down. You gotta keep it around. Plus, and I'm gonna write a huge bracket here, because almost every single year there are tons of people who forget to carry the sign here, and oftentimes the sign here could have been negative, and it would still be negative here, and then you'd still have to distribute it. Okay? It's a huge pain. Make sure you're keeping track of the sign, or at least make sure you're keeping a huge bracket here. Ultraviolet. I'm going to mix it up here just to make it look interesting. Computer freaked out there. Ultraviolet minus the integral of voodoo. And many of you might be weeping now. Weeping because it's still not over. The pain still doesn't end. You still have to do this integral. Yes, yes, yes. Wine, wine, wine. Let's just change colors to nice, because we're done. Alright. So maybe you're all sitting there thinking, what is that last one? Try to do it. It's the same as the ones we've done, sort of. It's at least very similar to those. La la la. Alright, so the integral of sine, the antiderivative of sine, is cosine. Not just cosine, it's negative cosine. Now, some of you may be realizing why I said it's similar to what we did before. Plus. Because it's right here, guys. We just did the integral together. The integral of sine is negative cosine, 1/2 because of the hook off. Depending on how you printed it out, you may or may not have space to do this problem again. Again? Again, you say? Yeah, again. We're going to do this problem one more time, a different way. Rahul likes to call it the tic-tac-toe method. You'll see why in the movie we watch at the end of the year after the AP test. It's also called tabular method. So let me do the tabular method here. Let me make sure I don't have a slide for it. Let me make sure my examples are, yeah, okay. My examples are definitely your examples. Cool. Good. So, yeah, and the advantage of this is if you were like, oh god, I wasn't done copying, you can just pause the video and rewind. Okay, tabular method. Get your own paper out. Got somewhere to write this down because this can make you extraordinarily fast. For the test I give on this unit, there is a problem that if you do not do it with the tabular method, you are dead in the water. No kidding. Alright, here we go. Tabular method. 3, 2, 1. So, this is used for when U is algebraic. And again, that's a fancy word for polynomial. Okay? Yeah, looks okay. Alright, here we go. Is U algebraic here? Yes? Well, we're going to have a U column. I'll make the columns real nice for you guys. No, not in red. Well, nah, not in red. U column. Do I want to have a sign column? Yeah, sure. I'll show you the two ways to do it. U column, a DV column, obviously. Oh, gross, sorry. A DV column. And we'll call this a sign column, although I see people do this lots of different ways. Okay? So, my U starts out as x squared. And I just differentiate downward. This is, differentiate until 0. 2x, 2, 0. Okay? 0. dv was what? Oh, it was, oh man, come on. It was sine 2x. And here's where you have to, integration skills have to be on point. Negative 1/2 cosine 2x. Negative 1/4. Keep track of your signs. It's harder in some respects for that reason. And then positive 1/8 cosine 2x. Alright. So the idea here is, after you've done those two steps, we do something like a sign column minus, plus, minus. It always alternates. It always starts with a negative. Always alternates. I never wrote down what the middle column did. Always alternates. Minus, plus, minus, plus. It's always the same. It's always the same. Always the same. This column, I'm sure you figured it out, integrate. And what tells you to stop? The 0. You just keep integrating until you get that. Alright, now, why is that helpful? I don't understand, Mr. Leven. This seems like a whole big jam up. Really? Why wouldn't it grab that? Right? Didn't I highlight everything? Well, that's amazing. Technology is the bomb. Wonderful. Okay. So here I go. I take this entry. I go down. I take this entry. I go down and to the right. Down and to the right. And then I have the answer. And then I have the answer. As long as I keep track of the sign. So I take a sine. And then what's the product here? X squared with negative 1/2 cosine 2x. Then I take a sine minus. It's not going to get nice. I doubt we're going to fit it. I'm sorry. Minus. Then I take a 2x. And I take a negative 1/4 sine 2x. I'm just going to shrink it one more time. Oh, now the table wants to come along. What a surprise. I guess it just doesn't shrink. Or it doesn't scale as it shrinks, probably. Okay. Anyway. Then one more time. Sine. What's the sign in this column? Oh, plus. Sorry. 2x. No, 2. Okay. You should be able to rewind and get the stuff that's getting off the board. So, there we go. 2 times 1/8 cosine 2x plus c. And you're done. So, that was more confusing because I kept having to shrink it and stuff. But in general, that's how fast it is. You're just done now. All you have to do is repeated integration, repeated differentiation, and then stick it all together. Boom, 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 boom. In the case, again, it's this one. We don't go down to the right again. Just straight across. Okay? That's tabular, and it's done. It's beautiful. It's great. It's wonderful. If you simplify this, you'll see we have the same thing we started with in the last one, or we ended with last time. All right. Now, life wouldn't be complete without a definite integral in this method. Now, don't get excited. This is not tabular. Tabular is completely optional. You can do every problem without tabular. On the BC test, you can do every single problem without knowing what the tabular method was. You just will have to do integration by parts again, which is its own special joy. Now, here we go. Integration by parts, clearly. Nobody taught you how to integrate natural log. I mean, you could look for it, took off 1 over x. I don't see a 1 over x around. And then power rule is a non-starter because this thing's an ugly mess. So, we do. U equal x squared. Du equals 2x. dv equals ln x dx. And then v would be what? Now, if you said 1 over x, you're not thinking about this. That's the derivative. How do I go from dv to v? I have to integrate. I have to integrate, guys. And that's not working. I can't integrate natural log. And what you'll notice is I was leading you down this path to see if you were paying attention. This is not right. Liate. What's the easier thing to differentiate? Maybe you think they're both easy. That'd be good. But what's the harder thing to integrate? The harder thing to integrate, as we just saw, was natural log. And again, the whole discussion's avoided with liate. L is the first one. Log is the first choice for you. Because of that. Because of how hard it is to integrate. du would be what? 1 over x dx. We did go over that. So that is u in this case. And now dv is the rest of it. This is the first one of today. There's many in your homework where you don't necessarily want to just do polynomial as u. It's not right. It's why the tabular method would not work here. If that's dv, then v is x cubed over 3. Okay. In class, I think I got a question like, why not plus c? Well, it's honestly because we're going to have all the constants at the end. In this case, it's also definite, so we don't have a plus c in general. But don't ever be adding a plus c here. That'd be wrong. It's all going to get looped in with a big plus c at the end. Here I go. Here I go. All right. U times v minus integral v times u. And we are simplifying. Oh, bounds. There are two ways to write bounds here. Two good ways to write bounds. Either you remember to do it here and here. And I don't like that. I do not like that. I think it's messy and easy to forget. So just remember, this is always going to be acceptable. You can just do it once on the outside. We're evaluating this whole thing from 1 to e. We're evaluating the whole thing from 1 to e. Whatever is going to spit out, we're evaluating it from 1 all the way up to e. I'm going to clean it up. Now, what doesn't clean up is this thing. You're going to keep that bracket there the whole time, guys. X cubed. It's a little more natural to write it this way. Minus, I'm going to bring out the third. X cubed over x is x squared dx. And again, this whole thing is still going to get evaluated from 1 to e. And now a sense of calm should come over you. I can do this integral, normal integral, nice integral, friendly integral. X cubed ln x over 3 minus integral of x squared is x cubed over 3. So I hope you do not object to me writing 1/9 x cubed. And now, do not forget to evaluate from 1 to e. Again, on the AP test, this is most of your points. Most of your points. Most of your points. You gotta go the extra step though, people. E cubed ln e over 3 minus 1/9 e cubed minus bracket. We're balancing this whole thing. 1 cubed ln 1 over 3 minus 1/9 times 1 cubed. And that's good enough for government work. Cool, 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 cool. All done. Hey, you should know, natural log 1 is 0. So that could have gone away. Natural log e is 1. So that could stay around. I mean, it goes to 1, e cubed, 3, blah. Okay? All right. Example 6. The hard one. The weird one. The one you want to start doing now, because it's been coming up more and more on the test lately, the AP test. So, you look at it. You say, is it parts? No, it's not parts. Wait, do your notes have it? Because I don't know if I made them do it without their notes. Give me a second, guys. One second. I have to look at my other computer. 6. La 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 la. Oh yeah, your notes tell you. Fine. I'll also spoil a surprise. Hey, we're going to do this with completing the square. Now, unfortunately, nothing else is really going to work here. And so that's the hard part of the BC test. It's a lot of techniques, so you have to really struggle, and one of them would be completing the square. So, in case you forgot about completing the square, the way I tell my Math 1 students to do it, we're looking at that polynomial. We say the b term, b is 4, so b over 2 equals 2. And that's the square everyone's talking about. So I want this. Want plus b over 2 squared. In order to complete the square, I want a positive b over 2 quantity squared. What's that going to be in this case? It's 4. So, the common technique, the way most teachers teach us, at least I hope, x squared plus 4x plus 8, the same old thing, plus 4 minus 4. Why can I do that? Because all I did was I added 0. All I did was to add 0. And then I slowly mix the parts around. X squared plus 4x. And now this imposter part replaces the 8. Plus 8 minus 4. And then we condense into x squared plus 4x plus 4, a perfect square plus 4. Okay? This hanger-on part. And the idea is of completing the square, and I know some of you are jumping up and down saying, shouting at the screen like, oh my god, that was so much harder than what you could have done. Calm down. The reason this is a complete the square, this is a perfect square. And who is it a perfect square of? X plus 2, quantity squared. And that 2, ladies and gentlemen, boys and girls, children of all ages, was that 2. So if you can do all this in your head, I'm so very proud of you. If you can't, you write it down, and that's always how completing the square works. That number there is always that number. Okay? This number is not that number. That was just random. And for those of you who cannot hold your enthusiasm, yes, you could have gone right from here to here. You could have realized, oh, I can make 4 out of 8. Like that. Okay. So now, this and this are equal. All of this is equal. That was a quick review of completing the square. It's not trivial. So this integral I started with is equal to this integral. And now some of you are like, well, that was a big waste of time. That didn't help me, Mr. Leven. I don't know how to do that. Well, I notice it's 1 over something with an x, even better, something with an x squared plus a constant squared. So in my mind, because I've been doing this long, in my mind, I see this as looks like 1 over u squared plus a squared, which is arctan. And just in case you don't memorize the rule yet. Okay? Oh, sorry, u over. Alright, so let's try to get that. Let's try to get that. Can't hurt. In fact, it's going to work out beautifully. Trust me. So, I don't know what color to use. U. So, we're talking about u prime. What do you call it? U prime, I'm sorry. Got 2 into the parts. U prime would have been 1. Excellent. Thing to hook off there. And a would have been, if this is a squared, 2. And then it is just arctan. So 1 over a arctan x plus 2. That's u over a mas capital C. Bingo bango. Oh mio, oh mio. Toledo, Ohio. I don't know. All right, so your integration skills are getting powerful. If you watch 6.2 and 6.3 this week, you've done what I've asked you to do, sort of. If you've done 6.2 and 6.3's homework assignment, if you've been able to do the homework for 6.2 and 6.3, you've done what I've asked you. And I know nobody wants to have extra homework assignments, But, right, we're talking about this for a while. It's either do all the homework now, slowly as we go, or do all the homework at the end. And if you're watching this on April 30th, well, I wish you luck. I really do. But it was probably a bad idea to sign up for BC if you were only going to watch this on April 30th. It's so strange to be talking to future you, I guess. I guess I'm talking to future you always. Always. You know, sound has a speed. And a philosophical rant. I'm very proud of you guys if you're keeping up with this stuff. Keep up the hard work. Tune in tomorrow or next week or whatever to see 6-3, which is certainly a technique you learn about in pre-calculus. Plus more. All right, guys. Have a great day. Bye.